All right, greetings YouTube, beautiful mind here. So what this lecture today is, we're at the end of our quarter system. So we need to get through the rest of chapter 2, which is like 3 sections. So I'm just gonna kind of touch on a few items. We have about right at an hour, so I want to spend no more than 20 minutes per section. So about 15 to 20 minutes per section. Okay. Anybody in the audience have any questions? Any questions about anything? Let's get a sense of these final days in this quarter. So the next time we meet, we have exam 3 over the first half of chapter 2. So that's 2.1, 2.2, 2.3, and 2.4. The study guide for that has been loaded in my math lab for at least a week or two now. Over the weekend, it's not there. Is it not? It is there. My math lab. It's on my math lab. Okay, so just kind of stop me at the end of class. Try to get me at the end of class, and let's make sure that it's there. Okay. Okay, so all of chapter 1 and chapter 2 is loaded in my math lab. The study guide for exam 3 is loaded into my math lab. So that's for this Friday. Honestly, if you're comfortable with my study guide, you should be okay for exam 3. I'm not trying to trick or anything. Open notes. You decide how you want to work that. I'm not going to print off a PDF. So I want you to access my math lab. So if you want the study guide, you need to log into my math lab, and it's there. Use that tool. People have been asking questions. It's fantastic. And I'll make the videos as soon as I can. But yeah, you just log into my math lab and make use of that tool. Okay? So that's for this Friday. Monday, we'll take some time to review for the final, right? We're going to review for the final. Monday, because the final exam is Wednesday, chapters 1 and 2. Okay? So we do chapters 1 and 2. That'll be Wednesday. By a show of hands, did anybody miss an exam? So if you missed an exam for any reason, I don't really ask any questions. You get a makeup day on the following Friday. What exam was it that you missed?
The first one.
The first one. Okay. So I'll be sure to have an alternate version of that ready to go. But that'll be that Friday after the final. So the final is that Wednesday. Is there some hour-long program or something that you all would like to watch? I wanted to get my hands on something. I have an idea, but it's huh? Something funny? You know something that's an hour long that's funny?
Scary too. Funny, but creepy and scary. I don't know.
Like Get Out? Have you seen Get Out?
Yeah, but I don't want to watch that again. So I'll have to watch it by myself again.
I'm not gonna play on
What about the movie? Oh, I love that movie. I like some.
Okay, so but it's only an hour, right? We only got like just about an hour, so we'll think about that. The focus for right now. Yeah, the focus for right now is exam 3 for Friday. Okay, so you have to do the best you can with that. The study guide is loaded. If anything is not clear on the study guide, reach out to me and I'll do my best. Okay. So that's Wednesday, and then Friday is the last day of next week. Next Fridays, that's it for the quarter. I have to get grades in immediately. Go ahead. We'll talk about a major extra credit opportunity after exam 3.
Okay, so that Friday it'd be me taking the test from 1.1 to 1.4.
Yeah, first half of chapter 1.
Okay.
Yeah.
You know the live videos that you stream. Do those extra credit opportunities have deadlines?
Yeah, so the ones on the weekends.
Yeah.
Yeah, those. Yeah. So just
The deadline the weekend.
I usually give it about an hour or so. So like I know I had one student live. So I mean just do it anyway. I mean the worst I'll say is no, nothing happens. I might say yeah, and then you might get the points. Okay, yeah. So I can't think of anything else. Any other questions, comments, or concerns before we get the party started? Okay. Check the time. Yeah, so we have right at about 15 to 20 minutes per section. So we'll go ahead and move into section 2.6, graphs of basic functions, okay? A function is continuous over an interinterval if its domain is, if its hand-drawn graph over the interval can be sketched without lifting the pencil. This is easier to see with the picture, with the graph. So it says, describe the intervals of continuity for the function. So if this is a parabola, tell me about the domain, the very left to the very right. Okay, that's fine. Tell me about the range, the very bottom to the very top. 0 to positive infinity sounds good. Now, What we mean by continuous in this context, give me a color.
Orange.
That's fine. That's fine. I heard purple. So now, if we start here on the far left and we start tracing the graph, notice we can trace the entire graph without picking our finger up or without picking the pencil up. So that's what we mean by continuous. So when you can trace a graph without picking up the pencil and get to all the points, that's what we mean by continuous. But if there are any gaps, breaks, holes, anything like that, then it's not continuous. So this function is going to be continuous over the entire domain of negative infinity to infinity. Again, these are typos here. This is supposed to be negative infinity to infinity. Okay. Questions, comments, or concerns? Let's keep it moving. Intervals of continuity. What's this? What kind of function is this? It's a straight what? For the most part, it's linear. Okay, notice if we were to trace this left to right, if we trace it, notice if we started here, we can get to any point going this way, agreed? Right? Because the arrow means continue the pattern, so we can get to any point even if we continue off the screen. But if we come here, it's not defined when x is 3, so we have to pick up our pencil and jump over that gap, and then we have to pick it up. All right, you see what I mean? Yeah. So this is an example of something that is not continuous. All right? Continuous means we can get to every point on the graph without, there are no gaps, holes, breaks. There's no break. When it's a break or a gap or a hole, that means it's discontinuous. Continuous means we can get to every point. We can trace the graph. We can get to every point on the graph without a gap or a jump or anything like that, right? Because if we can't go straight through that because it's not defined at 3 when x is 3. Does that make sense? So, like for instance, when x is 0, it's defined. When x is -1, y is here. When x is negative 3, y is here. What's the value when x is 3? See, that hole means that it's not defined. If it was filled in, then y would be equal to 1. But because it's a hole, it says you can get really, really close to that value, but it's not defined when x is 3. So there's a gap there. So this is an example of something that's discontinuous. So it is continuous from the left from the left side of 3 onto negative infinity, and on the right side of 3 on the positive infinity. But at 3 is not defined. That's a gap. So this function, as in and of itself, is an example of a function that's discontinuous. Let's see if they have more of an explanation. Okay. Did that help at all? Okay. Let's keep looking at examples. Let's keep working some examples. All right. So now we're getting into some basic functions. All right. So I don't know if you noticed, like when we kind of started getting these functions, and I kind of already had a sense of what the graphs looked like. It's because of this discussion here. The identity function. So let me clean up these notes. Do we have a better slide? No? Okay. So let me clean up these notes. So identity function, this is f of x equals x, right? The domain is negative infinity to infinity. The range is negative infinity to infinity. This graph is proper. This is basically just y equals x, right? So we get this diagonal line. So whatever x value you get, that's the corresponding y. Okay, so the graph is right. Now, as we trace this graph left to right, give me another color. Blue. Right? As we trace this graph left to right, as we go from the left to the right, is it going up, down, or staying flat? It's going up, right? That's what we mean. That's what we mean by increasing. So, as we trace in a graphical sense, as we trace the graph left to right, it goes up. That means the function is increasing. That's the simple explanation. Okay. So we say this function is increasing over the entire domain of all reals. So f of x equal to x is increasing over the entire domain of negative infinity to infinity. Any questions on this slide? We don't have much time, so let me kind of move forward. I'm going to turn up the speed a little bit. So this is y equals x squared. So this is f of x equals x squared. So what, from this graph, tell me about the domain very left to very right. Actually, we just did this one. So negative infinity to infinity, right? The range goes from 0 to infinity. Now, as we trace this left to right, if we start from the far left, you know, it goes further, but notice as we go left to right, what is it doing initially? It's going what? It's going down. and then it starts going back up. So it's decreasing from where? How far left can we go? Negative infinity all the way to where? All the way to 0 when x is 0. And then it increases from 0 to infinity. Now, one text that I was working from, it had these as parentheses. Because really, you're not, that book, the way they define increasing, decreasing, and constant, you couldn't talk about increasing, decreasing, constant with an endpoint. So I'm not going to be super strict on this right here. Again, one text I was looking at said that this is supposed to be a parentheses. You always got to have at least 2 points, and so at the end point, you can't really talk about it at the point of 0. But, you know, I'm not going to be super strict about that right now. If you're talking increasing, decreasing, constant, just do, well, it's going to be multiple choice. As far as I'm concerned, it's supposed to be parentheses, you know, but I'm not going to be strict about that part. Okay, so I'm not going to be strict about that right here. Just for increasing, decreasing, and constant. Because I have conflicting things. Again, negative infinity to infinity for the domain and range. This is the cubic function. Give me a different color. We have f of x. Can y'all see that at all? F of x, this is going to be x to the power 3. So these are all basic functions that we're going to be working with. Notice the first one was f of x equals x to the power of 1. Then we looked at x squared. Now we're looking at x cubed. What can you notice about when the highest exponent is odd versus when it's even?
When it's odd, it goes more in one direction. When it's even,
That's essentially it. Okay. So when it's odd, the long-term behavior is going to go in opposite directions. So when the highest exponent is odd, if you were in the audience right now, you can see me, you know, doing these math poses. I can show you this. I gotta find the image. It's called math dances. Anyway, when the highest exponent is odd, they're gonna go in opposite directions. When the highest exponent is even, like x squared and x to the 4th, they're gonna go in the same direction.
so I said it backwards.
You had the idea. I know you had the idea. But yeah. Okay. I'm gonna let that be for now because we're almost out of time for this section. Square root function. So this is going to be y equals the square root of x. This is really just the top half of a sideways parabola. So the square root function is the top half of a sideways parabola. Now, let's look at this image really quickly. What's the domain? Tell me the very left to the very right. It starts at 0, right? If we look at the x-axis, as we go to the left, it starts at 0, right? When x is 0, right? And then how far right does it go to?
It's not positive infinity because it's got an arrow in it.
It's an implied arrow. This is a typo. It is supposed to be an arrow. Yeah. Positive infinity. Yeah. Let me go ahead and do this. These are all supposed to have arrows. But yeah, so so the domain, the very left to the very right, it goes all the way to the left of 0. Okay. What is that for? Oh, okay. I appreciate you. I appreciate you. Yeah, I got you. Ooh, I like that. Okay. Okay. So the very left to the very right, going to the left, x starts at 0. Going to the right, it goes off to positive infinity. That's the domain. So about the range, how far down does it go on the y-axis? How far down does it go? Okay. 0, right? It's still 0. If you look at the y-axis, so let's do this. Give me a different color. Okay, we'll do this green, right? I'm going to go here. Okay, and then let's go like this. We're going to go style. We need a thicker line, something I can see. I think that's a little bit better for this one. Okay. So now, when we're doing range, the range is the very bottom to the very top. So how far down does it go? What's your y value here? 0. What's the very top? How far up does it go? Infinity, right? Is y defined here? What's the y value here? Where is it going to be? Way over to the right. Remember, we got to use your imagination. The arrow means continue the pattern. So if the pattern continues, it's going to go off screen, but eventually the y value is going to It's gonna crack. It's gonna cross. Does that make sense?
Yeah.
So you just got to use your imagination. Okay, just making sure.
It's going straight and it's still going up.
Yeah, sometimes students will do like this. They'll say, "Oh, it stops at 3." They'll say 3. So you got to know that it keeps going up. You got to use your imagination. So, okay, that was good. So the range we said was from 0 to infinity. All right, tell me about increasing, decreasing, or constant. As we trace it left to right, what is it doing? It's going up. It's going up. It's very slowly going up as we trace it left to right, right? Right? It's
What do you mean from left to right?
left. So the far left, if we start here, from the left, over here, as we trace it left to right, is it going up or is it going down? Yeah. Yeah. Okay, is that okay? That's okay. That's okay. That's why we're here. That's why we are here. Oh, I got a message. Oh man, people are clamoring. I probably need to do that. Okay. So it's increasing from where to where? 0 to positive infinity. Okay. Okay. Questions, comments, or concerns? I'm going to move forward. This is the cube root function. Okay. Oh, so now why is it? Can somebody tell me why is it that the square root goes from? We can only take the square root from 0 to infinity. Because why is the domain of the square root from 0 to infinity? We can take the square root of 0, but we can't take the square root of. We can't take the square root of negative numbers, right? What's the square root of 0? Because 0 squared is 0, right? What's the square root of 4? Because 2 squared is 4. What's the square root of 1? 1 because the square 1 times 1 is 1. What's the square root of 9? You see that? So now, if we tried to take the square root of a negative, it doesn't exist in the reals because you can't square a real number to get a negative result. So that's why we created. That's why a whole nother system was created called the imaginaries. Imaginary system or whatever, complex numbers. So that's a whole different system. Anyway, okay, I think that's it there. Cube root function looks like this. So these are all basic functions that we're going to play on. So we're going to start with these basic functions and then do manipulations on them. Give me just a moment. Okay, yeah. And this is a classic one, absolute value. Really quickly, tell me domain very left to very right. Negative infinity to infinity. What's the domain? The range, the very bottom to the very top? 0 to infinity. Is the function increasing, decreasing, or constant? Okay. As we start from the far left, what is it doing first? It's decreasing. It's decreasing from where to where? Negative infinity to 0. You cannot leave. No, I'm playing. I don't know. It's kind of creepy. It's like, is it unlocked? Pull it in, and then, there you go. Okay. That's kind of creepy. That kind of, it used to, stuff like that would irk me. Like a locked room like that. In the past, I used to be claustrophobic. I learned how to calm down. Yeah, I know how to work the door. But in the past, stuff like that would have made me kind of panic a little bit. But now it's like, okay, I know to just breathe. And then usually if you can get yourself into something, you can get out. Everything that has a beginning has an end. So there's always a way. Okay, so as we trace it left to right, initially, what is it doing? It's going down from negative infinity to 0. Then from 0 to infinity, what is it doing? Any questions there?
I saw a problem like this on the spin guide.
Mm-hmm.
Oh.
Yep, the origin, yep. Okay, so the vertex, yep. So this is absolute value function, right? So y equals absolute value of x. It looks like this. It's a v. All right, I'm going to move forward. So graph this function. It says negative 2x plus 5 if x is less than or equal to 2. Now, if we didn't have that x is less than or equal to 2, we're about out of time for this. If we didn't have that second part, what would the graph be? It would be a line, right? What's the y-intercept? 5. What's the slope? Negative 2, right? So it would be a line with a negative slope passing through, a slope of negative 2 passing through y equals 5. But then it says we only want the graph if x is less than or equal to 2. So we would graph it like normal, and then if we want less than 2, are we going to erase things to the left of 2 or things to the right of 2? So let's look at that again. If here, let me rework that. If x is less than or equal to 2, do we keep the things to the left of 2 or the things to the right of 2?
To the left.
We're going to keep everything to the left of 2, right? Oh, and then there's a second part. I didn't see that. So now the second part is, again, it's another straight line. Tell me about the y-intercept. 1. Tell me about the slope. 1. So y-intercept of 1, slope is 1. But this one, we're going to keep when x is strictly bigger than 2. So do we keep everything to the left of 2 or everything to the right? So again, so now this is called a piecewise function. All you do is do the graph like normal, but then the second part or the conditions tells you what to get rid of. Does that make sense? So just graph it like you normally would. This is going to be 2 graphs in one plane. But then the second part tells you what to keep and what to get rid of, right? So if we look at it, you see the first one we said a line with negative slope. Y-intercept is 5, it has a slope of -2, and we kept the left part. The second one says it's a straight line, a slope of 1, with a y-intercept of 1, but it says keep the numbers to the right of 2. So we get a graph like this. Is that clear? Any questions there? Again, this is called a piecewise function. So that takes practice. Be sure that you can do this, okay? It does trip students up sometimes. What is the graph of the first one going to look like? It's a straight line. What's the y-intercept? 3. What's the slope? It's a positive slope, right? So as we trace it left to right, is it going to go up or is it going to go down? It's going to go up. If x is less than or equal to 0, do we keep the numbers on the left of 0 or on the right of 0? The left of 0, right?
Wait, if x is greater than 0.
No, the first one said x is less than or equal to 0.
Oh, no.
Yeah, so the second one now, what's the graph going to be? What's the highest exponent? 2. So it's a parabola. Does it open up or does it open down? Why did you say down?
It's negative.
What's negative? The leading coefficient is negative, yes. The leading coefficient is negative, so this is going to be a downward, a parabola that opens down. Tell me about the y-intercept. 6, that sounds good. Are we going to keep the numbers to the left of 0 or to the right of 0? Right, because x is bigger than 0. Any questions there? So the first one is a straight line with a positive slope. The second one is a downward-facing parabola. We're just gonna keep the right-hand side of that. And when you put those together, we get this image. Is this okay? I feel like this should be okay. So I want to kind of wrap this up. Greatest integer function, it looks like this. So the notation looks something. Give me a color. Blue, right? So the greatest integer function looks something like this. F of x, you got x, you got this kind of symbol. Something like that, right? This is the greatest integer. So this is the greatest integer less than or equal to your number. For instance, so if we have 2.5, I'm going to choose 2. If I have 2.1, I'm going to choose 2. We're going to take the integer less than or equal, basically the integer to the left. For instance, what I mean by that is this. This is what I mean.
So is that like absolute value with brackets?
Just watch. Oh, yeah. That's what it looks like, but the graph looks different, right? So say this is 0, -1, -2. This is 1, 2, 3, right? So if our x is 2.5, that means y is going to be 2, right? So when x is 2.5, anything from here to here collapses to 2. Any x value in there, the corresponding y is going to collapse to 2. It's like a floor function where you take the integer to the left, right? So for instance, if x were 3.5, what would be your y? What's the integer to the left? 3, right? If x were 1.1, what's your y value going to be? 1. If x were 0.69, what's your y? 0. If x were a -1.8, what's your y? -2, the number to the left. You see that? If x were a -1/2, what's your y? -1. It's the number to the left on the number line. Yeah, -1. So see, look, here's -1, -2, so -1 point something is here, right? What's the integer to the left? right here, -2. Okay, that's why I was doing that. Yeah, that's why I was doing that because I wanted to prime you with the easy part, and then see if you can continue the pattern on the not easy part. All right. So with all of this, there's a pattern. Once you get the pattern for the simple things, do the exact same thing when you get to something different, and see how it works. Because there's little things. So once you get it in the simple case, the complex is the exact same thing. Do the same thing and then try to pick up on the changes. Okay. So let's see. So when we put those two ideas together with the greatest integer function, we get something that looks like this. This is called the step function or the greatest integer function. Again, now watch. When x is 3.5, right? What's the corresponding y?
No.
Yeah, that's right. 3, right? You see it? When x is 4.2, what's the corresponding y? 4, right? See it? You see it? When x is 1.5, what's the corresponding y? Notice the number to the left is 1. I think these dots might be. Okay. So when x is a negative 2.7, what's the corresponding y? -3. The number to the left. You see that? Is that okay?
So it's just the number to the left.
On the number line.
On the y.
On the x.
The number to the right.
It's the number to the left.
Number to the left on the x-axis, but you put it to the one on y-axis.
Yeah, the y, the answer for y is going to be the number to the left. So for instance, if we say if x is 2.2, if you look on the number line, what's the number to the left? 2. So that means y is going to be 2.
So y is going to be 2 instead of 1.
Okay, that's called this is an example of a step function or the greatest integer function. I'm going to leave those marks.
That's not hard.
It's a little funky, but I agree it's not difficult. But the graph looks something like this, where it looks like a staircase. Okay. Also, I think this is supposed to be switched around. Usually, like for instance, if it's 1, then it's supposed to go to 1. Oh, no, this is right. This is right. When x is 1, so if you're on the integer itself, you take that integer. So for instance, if x were 4, then y is going to be what? 4. If x were -3, y is going to be -3, right? So when you get whatever number you're on, you take that number. Does that make sense? Okay. But if it's a decimal, you take the integers to the left. The integer to the left, yeah. Okay. This is called the greatest integer function or a step function. Greatest integer function, okay? So we worked some examples there. I'm going to have to leave this as an exercise. I don't have time to do the rest, okay? It's a good idea to go through these examples and make sure that you're comfortable with it. I'm going to let that be. So I think that concludes what was that? 2.6. Let's go ahead and take a look at 2.7. So I'll go back to our Moodle page, go back. 2.7 is here. I am so sleepy. Share, copy to Notability. And I would like to, I probably should create a new note. Yeah, let's just create a new note. It's a simple thing. That way it doesn't get overloaded. And then I need to actually go back to 2.6, the previous one that we just did, which is this one. I need to load this in the box. I'm going to share the box. Winner. This is college algebra, entire course, notes, and right there. So on that bar loads, you'll get a copy of anything that you saw me writing. This works for the people listening at home as well, my other students. But anything that you see loading, when this bar loads, anything you saw me do, you should be able to get a copy of it. So we'll take a moment and let that load. So do y'all have any questions about anything before we move forward? Okay, so I'm going to move into 2.7. Give me just a moment. Feel myself getting sleepy. So I'm already in like vacation mode. This happens to me like the end of every little session we have. I just feel it coming, and I just like my mind. I'm thinking about where I want to travel, if I want to go to the beach, if I want to go across the country. That's where my mind goes. So I'm not even really like here. I'm just trying to do whatever I need to do, and then I'm on my way. Okay. Anyway, give me just one moment. Okay. So not too bad. So 20 minutes from now will be 12:50. If I can keep it to 10 minutes, it's ideal. I'm not going to be able to keep this to 10 minutes. So about 12:50, I'm going to stop. And then I got to go to the next one. So now graphing techniques. So now we're going to take those basic functions that we were just exploring and do some manipulations on them. These manipulations, you can verify all of them with like creating a table, plotting points, right? Is that okay? So these are some of the techniques, and let's take a look at them. We're asked to graph this. Now, what does the absolute value function look like? It's a what? Remember, absolute value? What kind of shape?
Oh, yeah.
It's a V, right? Okay, let's look at it. Let's just look at it. Okay, so we can make a table, right? So we just chose some values of x on the left. This red is supposed to be f of x. Oh, even my pen is not working properly. Maybe if I make it thicker, it'll behave better. Nope. I'm not liking that either. Oop, I don't know what's going on with the pen. But anyway, so f of x should be equal to absolute value of x here. And then g of x is, again, absolute value. It's supposed to be g of x 2 times the absolute value of x, right? So now, the one in red, we saw that one already. And let me just kind of get rid of this. So the one in red we saw already. We know it's a v. We chose some values of x. We found the corresponding y. For instance, what's the absolute value of negative 2? 2. What's the absolute value of negative 10? What's the absolute value of 3.5? Okay. So absolute value is just a positive distance away from 0. So then the second one, we have 2 times absolute value, so we doubled up all those results. Okay, so if we plot it, now what do you think is going to happen with the graph? If we have a V, what kind of distortion do you think is going to happen? What do you think it might happen?
It's gonna shrink.
What'd you say? You said shrink. What made you say shrink? I'm just curious. Okay, that's fine. Yeah, what you... She said it's going to get more narrow. She said shrink. You mean like something like this. Okay. Yeah, no, it's okay. Because I'm just trying to get a sense of your intuition. So now, let's look at it. So if we were to plot these points, the red versus the blue, notice, the red is the original, the blue is the new. You said shrink, right? That's why I say... So this is all about... I'm all about intuition. And the only way your intuition gets stronger is if you go with it. You ever heard, oh, I shouldn't second guess myself, or I should go with my first mind? Go with your first mind. Whatever your first mind is, more often than not, is right. The more you go with your intuition, the more accurate it'll become. But if you're always constantly second guessing yourself, it's going to be weak. But if you practice, oh, well, my first mind said this, so that's what we're going to go with, it's going to get stronger and stronger and better and better. It's going to become more accurate. When you first start doing that, it's not really going to work. But the more you do it, the more accurate it'll become. So your first intuition, your first mind said it's going to shrink. That was actually correct. That's why I was encouraging you to do that. That was a smooth little move. Did you see that? She just came out of nowhere from out on the table. That was like awesome. I was like, where did she come from? So anyway, okay. So yeah, so that was awesome. So, yes. So now, we have our basic function, and we multiplied the outside by a number larger than 1. Let me think about it. Yeah. So, she said it shrinks, right? So now, when we multiply the outside of our function by a number larger than 1, it's correct, but instead of shrinking in a horizontal sense, what we're really doing is called a vertical stretch. So we're stretching it vertically. Outside manipulations are vertical manipulations. So this is an example of a vertical stretch. So if we have a V and we stretch it vertically, it will become more narrow. If you think about like Laffy Taffy, you ever worked with Laffy Taffy or Putty or anything? Oh, yeah. And if you had an image on there and if you stretched it, it became skinny, right?
So bigger than 1 is going to shrink.
Okay, wait. So the thing is, if it's a number larger than 1 on the outside, it's going to be a vertical stretch. A vertical stretch is the same as a horizontal compression. Okay, right. So where your intuition said it's going to shrink, you were talking about horizontal. That's correct. But what's really going on, outside manipulations are vertical, right? And so outside and larger than 1 means a vertical stretch. That's the first one. So if outside and larger than 1 is a vertical stretch, what do you think happens if it's outside and between 0 and 1? That's exactly right, right? So larger than 1 and outside is going to be a vertical stretch. So if it's outside and between 0 and 1, it's going to be a vertical compression. It's like all the y's get cut in half or by some fraction. So the y goes from 2 to 1.
So when you saying the outside, you're talking about the 2?
Outside of the basic function. The basic function is absolute value, so we're on the outside of that function. Versus if that 2 were inside the absolute value of x. Let's keep going. You'll see it. So this is still only the first example. All right, so this is the next one, right? So notice, we're doing a manipulation. What's the basic function, first of all? Absolute value, right? The basic function is absolute value. So what's the basic shape? It's still a v. Now, notice, in the last time, we multiplied the outside by a number larger than 1, and it was a vertical stretch. So intuitively, if we multiply the outside by a number that's less than 1, what should happen? It's going to be a vertical compression. It will get wider, but you're going to smush it vertically. Again, outside manipulations are vertical manipulations. So a number less than 1 on the outside or between 0 and 1 on the outside is going to be, they're going to smush it vertically, right? So it's going to get wider. It's going to smush it like this, right? So, right? So then the red is the original. Now notice the new one was smushed and it got wider, right? All right. So we looked at multiplying the outside by a number larger than 1. That was a vertical stretch. We multiplied the outside by a number between 0 and 1. That was a vertical compression, right? So outside manipulations tend to follow your intuition. Riddle me this. Let me get a sense of what's next. Okay, so we're still on multiplication. Okay. So now, if outside means vertical, that means more than likely, intuitively, inside should be what? Horizontal. Does that make sense? So if outside manipulations are vertical manipulations, then intuitively, inside manipulations should be horizontal manipulations. Now, let's see how this goes. So here. So again, what's the basic function here in this next example? It's still what? It's still absolute value of x, so the base function is still the v. Now, if outside manipulations are vertical manipulations, then inside should be what? Horizontal. Since the inside is the opposite of the outside, notice that play that the opposite word I just said. So now, on the outside by a number larger than 1 is a vertical stretch. So now we're inside, so we know we're talking about horizontal. What do you think is going to happen? What does your intuition tell you based on this conversation we had? Okay, so it's actually the reverse. So inside manipulations is the reverse of your intuition. Intuitively, the number's larger than 1. It does make sense for you would think it would stretch horizontally. But what's actually going to happen, you're going to do a horizontal compression. A simple way to keep this in mind, if you're multiplying by a number larger than 1 where there's inside or outside, it's going to get tall and skinny. It's going to just keep it. Because a vertical stretch is the same as a horizontal compression. This is a horizontal compression, which is the same as a horizontal stretch. Sorry, vertical stretch. Does that make sense? So you said, what was your first mind? What did you say initially? Yeah, it's going to get, but it gets smaller vertically. In the horizontal, sorry, wait a minute. I keep getting this back. The whole point is, this is how it goes. Outside manipulations are vertical manipulations. If you're on the outside, it follows your intuition, right?
Okay, you said outside is vertical.
Outside is vertical, so that means it's all about up and down. If we're on the outside, it follows your intuition, right? So if we multiply by a number larger than 1, then what would you expect to happen? It should get what? It should get bigger. It's going to get bigger. It's going to stretch in a vertical sense, right? If we multiply by a number between 0 and 1 on the outside, it's going to do what? It's going to get smushed in a vertical sense, right? But now when we start working on the inside of these functions, it's the reverse. It's horizontal. It's going to be the reverse of your intuition, right? So now, intuitively, because 2 is bigger than 1, intuition might say, oh, we might get bigger. It's the opposite, right? So in a horizontal sense, it should be a horizontal compression. Okay, does that make sense? Intuitively, you would imagine the horizontal would get bigger, but it's actually the opposite. So it should be a horizontal compression. And then, but keep in mind, a horizontal compression is the same as a vertical stretch. So you can make a connection there if you want.
Okay, wait. I want.
Sorry, I forgot that they're listening, so I completely forgot about that. Go ahead. Yeah, because we can hear them, they can definitely hear me. because I be yelling like at the top of my lungs.
Okay.
Go ahead.
Outside, if it's bigger than one, it gets taller. If it's
It gets
smaller
bigger. Taller is fine, yeah.
If it's smaller than one,
But
it's
between 0 and 1.
between 0 and 1.
Yeah. Because negatives have a...
Not negative,
Yeah,
right,
yeah,
it's not negative.
yeah.
But if it's inside,
It's the reverse.
wait.
I'm sorry, go ahead. Go ahead, I'm sorry.
If it's inside and it's bigger than one, it gets smaller this way.
Horizontal compression, yes.
But if it's dang, I just
Between
said,
0 and 1.
if
It's the
if
reverse.
it's bigger than one inside, it gets smaller.
Yes.
This way. But if it's smaller than one inside, it gets bigger.
Yes, that's right. You got it. I know it's a little bit of a challenge initially.
I can see it, though.
Right, yeah, that's the whole point. And that's what I'm playing on. I want you guys to get this visual, this sense. So that way when you start working it, it'll sink in. And again, this is not going to be on exam 3, but this is fair game for the final. Okay? Let's keep moving. So officially we're good, we're okay. If I can wrap it up, that'd be great, but I'm going to keep moving. What is going on outside? Sounds like a helicopter to me. But anyway, so again, intuitively, 2 is bigger, so you would imagine it'll get bigger, but because it's inside, it's the reverse. And because it's inside, that means horizontal. So it should be a horizontal compression. Does that make sense? Let's see. So the original, we don't have it? Well, yeah, you just verify. Just verify that it works. Okay? So outside follows the intuition and is vertical manipulations. Inside is the reverse of your intuition and is horizontal manipulations. All right? Okay, that's enough for that. I'm going to let that be. That's all that this is saying. I'm going to let you go through this on your own just for the sake of time and just to keep it simple. But the conversation that we had just now is the best explanation for this slide. So just to kind of a quick recap. If we multiply the outside of our basic function by a number larger than 1, it's going to be a vertical stretch. If we multiply the outside of our basic function by a number between 0 and 1, it's going to be a vertical compression. It's going to get smushed. If we multiply the inside of our function by a number larger than 1, it's going to be a horizontal compression, right? If we multiply the inside of our basic function by a number between 0 and 1, it's going to be a horizontal stretch. Does that make sense? And to kind of bring these ideas home, keep in mind that a horizontal compression is the same as a vertical stretch. So you can look at it that way as well. Keep in mind that a horizontal stretch is the same as a vertical compression. So you can use that too. I feel like I'm doing Tai Chi over here. Is it just me? But, okay, so keep that in mind. So now, that's multiplying by numbers. Let's look at, next should be negatives, how multiplying by negative affects our graph. So we talked about both of these, so I'm going to let those be. Now, think about this. Say, let's imagine y equals x squared. What's that graph going to be?
If it's squared, it's more like that.
A parabola, yeah, U-shaped graph. Which way does it open? Up, right? So now, say we multiply the outside of our function by a negative. So all the y's go from positive to negative. Which way is it going to flip? It's going to flip up and down, right? So if we multiply the outside of our function by a negative, what we're essentially saying is that all the y's go from positive to negative. All right? Does that make sense? The x's stay the same, but the y's go from positive to negative, right? So when we multiply the outside of our basic function by a negative, it's going to flip up and down. Again, outside manipulations are still vertical manipulations.
Oh, so
see that?
All connect.
Yes. That's the whole everything that we're talking about. I'm painting this whole big picture. I'm trying to get as much details into your psyche as I can because it's part of a big picture. Now we're still not really thorough. We're only about halfway through what we really need to talk about. But I really want you to be proficient in what you know. So when you kind of move forward, honestly, if you plan on going forward in math, we did 1 and 2. You should probably go ahead and keep studying 3 and 4. If you did that on your own and you had questions, even after the quarter is over, I'm still willing to answer questions. And to be thorough, it's a good idea to go ahead on your own to go ahead and learn chapter 3. Go ahead and learn chapter 4. Even once we leave this quarter, to be complete. So if you get into pre-calculus or anything beyond college algebra, which you most definitely will, go ahead and look at chapter 3 and chapter 4. I'm trying to get my rhythm down to make sure we touch on what we need to, but I didn't want to overwhelm you with information overload. College algebra, the drawback is information overload. for most students. So I do the presentation the way I do because I'm trying to get people past their anxiety. Once you release the anxiety, then you can actually start to learn. But if you hold on to your anxiety, you keep saying things like, "Oh, I don't get it," or "Math is hard." I was like, that's not true, because it's easy. It's just boring, and but you actually already know it. So that's why I'm doing this whole presentation. Go ahead. The function, yeah. You'll see it. We're gonna keep working examples. So let's get some more examples, and it'll start to sink in. So now, okay. So now, outside manipulations are vertical manipulations. When we multiply the outside by a negative, it flipped up and down. What do you think happens intuitively if you multiply the inside by a negative? It flips side to side. See, this is how your intuition works. Thank you. Thank you. Somebody gets it. For the people at home, we got like a room split by a divider. So the other room, I guess they're doing presentations and they're applauding and clapping. It feels like they're applauding for me. Yeah, the timing is really funny. So anyway, I'm going to keep moving. All right. So now let's get a sense. Let's get going. Reflecting. Yeah, so we just said that. Okay, right here. So now, if we ignore the negative here, what was the basic function? What does the graph look like? What does the square root of x look like? The top what? Top half of sideways parabola, right? So if we were to ignore that negative, this would be the top half of a sideways parabola. Intuitively, now that we introduce the negative on the outside, what do you think the graph looks like? The bottom half of a sideways parabola. See that? Okay. How could you verify that this is the case? Choose what? Values of... Okay, you actually could. She said y. That's fine. See, that's your intuition. Your intuition said choose values of y. I actually think that's a much better thing than what I was about to say. Intuitive. So, for instance, let's just see this. I was going to say choose values of x. In this case, honestly, choosing values of y would be easier. Let me show you what I mean. So if we have y equals negative square root of x, right, and we created a table. So we said x and y. So you said values of y. I'm just going to start at 0. So if we say y equals negative square root of x, can you tell me what x equals? If we set y to 0, what's the corresponding x? If we solve for x, what would we do first? Yeah, so we can like either multiply or divide both sides by a negative, right? I need a thick, right? And it's still going to be 0.
So it's 0, right?
So we're going to have 0 equals the square root of x, right? And then how do we get rid of the square root? Square both sides, so then 0 squared. It's okay. It's okay. Because words get in our way anyway. Like, no, on the real, because that's called lost in translation. I know, I get a sense. I know you know what you're talking about. I can tell by the way you're responding. But honestly, the vocabulary gets in the way. Because, you know, if, for instance, if you brought somebody in here that doesn't speak English and you show them this, they don't know what I'm talking about. But then, oh no, this. But if you were to bring somebody that doesn't speak English and you show them this symbol here, they know what that means. If their account is like that, or if that 0 is on the left side of decimals and you got a number in front of that, everybody knows what that means. So the more powerful communication are symbols over letters. Letters are quasi-symbols. Apparently, the first way that we communicated was in symbolic form, and that was a lot more powerful. So that's why people like Prince and all these artists, that's why they're so timeless, because they emphasize symbolism. You know, when you see the symbol of the artist formerly known as Prince, it has a different meaning, but you get this sense of this savant, or whatever it's called, where he could play all these instruments. He could play the whole thing. You know, it's this energy behind it. You know, if I showed this symbol, for instance, if you don't speak English and I wrote this, you might not know what that means. But if you don't speak English and I wrote this, maybe something like, I don't know. Of course, you know that's what I'm about to do. Right? Something like that. My bird is awesome. Anyway, it's been a while, right? But if you didn't speak English and I drew this, you might think what? You might think bird. You might even think plane. You might think arrow. You see what I'm saying? So if you don't speak English, you might not know what that word means. But this symbol is more universal than the language. So that's what I mean by. So that's why I got into mathematics in the first place, because math is nothing but a language. You guys are now at another level of the language of mathematics. It's a language. So this is a language class. Is this music? I'm coming. I see your hand. But again, so I'm just showing you what the symbols mean. Okay, but it's all the same thing. So if you don't like math and you like reading, you actually like mathematics. I see it. I'm watching the clock. I know. I'm watching it. If you don't like math and you like music, you actually like math because math is like is frequency and pattern recognition and rhythm. That's what mathematics is. If you don't like math and you like dancing, you actually like math. If you don't like math and you like video games, you actually like math. If you don't like math, and you like technology and iPhones and all this stuff, you actually do like math. That's the whole point that I was trying to get you all to see. You actually already know this stuff. You just don't know that you know it. My job is to remind you of your divinity. Show you, hey, release your anxiety, release your fear. Unless that fear is protecting you and serving you and allowing you to grow, it might be protecting you, but it also might be stopping you from your greatness. You see what I'm saying? So don't let the fear and anxiety get in your way. Don't let it stop you from doing what you need to do. You see what I'm saying? You already know this stuff. Go ahead. Go ahead. Thank you for keeping me track. So let's finish this out because I know I started and I kind of went off track. So if y is 0, x is 0. Say y is 1, what's the corresponding x? So if y was 1, right? Negative square root of x. Divide by negative. On the left we get this, right? When we square both sides, what happens? X equals 1, right? Okay. Negative 1, right? So, sorry. Right there. Just like that. So we let y... Wait a minute. No. Stop. Wait a second. Give me a second. If y is 1, this isn't right. Hang on. So give me a moment, because this isn't right. Something's not right. Hang on. Give me a moment, because I'm moving kind of fast. Okay, so we said, but it's not really the case. I can try it. Let me see. It shouldn't work, though. Yeah, we're actually not doing it right. Yeah, there's actually more to that story. So this is why we're having this discussion. So sometimes you can do that, sometimes you can't. There's actually more going on here. But again, the simple thing is, we know square root is the top half of a sideways parabola. When we multiply the outside by a negative, it should flip up and down. So you should get a sense of what the graph should look like, okay? Hang tight, I see you, I'm coming. So then, when you put it together, we get an image like this. So the red is the top half, is the original. The blue is when we multiply the outside by a negative. We got the result that we were looking for, right? These are two different graphs on the same plane. The red is the square root of x. The blue is the negative square root of x. Remember, we said square root is the top half of a sideways parabola. So then if we take the negative half, right. You see that? Okay. Okay. All right. So now I'm ready for questions. I know you had a question. Did it get answered, or this is why I was kind of trying to wait. Yeah. Okay, I'm going to move forward.
But the positive parabola is that way, right?
The positive is the red. The negative is the blue.
No, when you said it's sideways, the positive won't go that way, right?
To the right, yeah. It opens to the right. Okay, let's keep going. So I know the time, we're pretty much out of time for this one, but that's okay. I want to kind of keep going with this. All right, so now we multiplied the outside by a negative and flipped it up and down. So what do you think is going to happen when we multiply the inside by a negative? Flip side to side. Now, if the negative were not there, what would the graph look like? What color do you see on the screen that it would look like? It would look like the red part, right? When we multiply the inside by a negative, the red is going to flip which way? Which way? Side to side, right? It's going to flip from the right to the left. Right? So if we do this, let's look at it.
You said on the inside?
Right. You see, the red is the original. Now the blue is the new.
Oh, okay.
So we flipped it side to side. So it still follows the same pattern that we had before. And you can verify all of these results. Okay? It's a little bit of a lot. It is information overload. This is, yeah, I know, right? Like a driveway and a what is it, driveway? You park in a driveway and drive in a parkway. That's why English language to me, yeah, like it makes no sense. Like we drive in a parkway and we park in a driveway. It seems like it would make more sense to drive in a driveway and park in a parkway.
Our feet smell
Nose and a nose runs. We
Cook
cook cookies and bake bacon. We bake cookies and cook bacon.
Yeah.
Well, we should cook cookies and bake bacon. That's dope. I'm about to borrow that. So one of my students said she called those she called them 420 questions. But basically she'll be like if you drop so but if you do a YouTube search, they're called weed questions or whatever. Or stoner questions. They're called stoner questions. If you drop a bar of soap on the ground, is the soap clean or is the floor dirty? Sorry, is the floor clean or is it soap dirty, right? How do you throw away a trash can? Because if you put a trash, like say I have, well, if you have a trash can and you put it out for the trash, but how do you know? So if I have a curb and I want to throw the trash can away, I can't just put the trash can on the curb, right? How do you throw it away? It's a stoner question, so it's not even a real question. There's a ton of them like that though. But yeah, we bake. Why don't we bake bacon and cook cookies? It's like we bake cookies and cook bacon. That's so funny. What is it? Fridge? There's a D in fridge, but no D in refrigerator. See, I don't. Okay. I know the answer. I'm not gonna say it.
My name.
No, I know the answer. I'm not gonna say it.
What comes twice in a week and once in a week?
My age.
Nope, I'm not gonna say it. I know it. I'm not gonna say it.
Sunday.
I'm gonna leave it be. Riddle me this. What gets wetter as it dries?
Huh?
Okay. What eats to live but dies if it drinks? Mm-mm.
Wait, what's the first one you said?
The first one I said, what gets wetter as it dries?
What was it?
A towel. Right? Okay.
Um,
What eats to live but dies if it drinks?
Vampires.
I'm gonna let that one be, so I'll let you figure that one out. And this is the last one that I'll do, and then we'll get back on track. Let me see. Always old. No. Let's save that one. Let's do this one. What's greater than God, more evil than the devil? The poor have it, the rich need it, and if you eat it, you'll die.
Oh, I heard that one.
Don't say it. If you know it, don't say it. Let them do it. Let's look at it again. What's greater than God, more evil than the devil? The poor have it, the rich need it, and if you eat it, you'll die.
Oh, the poor
Humility.
What'd you say?
Pride.
Mm-mm. So one more time. What's greater than God, more evil than the devil? The poor have it, the rich need it, and if you eat it, you'll die. The answers to any of these by the end of class today, I'll answer. So if you want to write, but don't look them up. That's going to ruin it. Don't look it up. See if you can figure it out. And I got one more. There's one more. Please don't look it up. That's going to ruin it because that's easy to do. I'm trying to activate some of your axioms and things in your brain. So there's one more. This is the last one that we're going to get back on track.
Wait, no, I got one.
Wait. There's one more, and then so here's another one. Another one goes always old, sometimes new, never sad, sometimes blue. Never pushing, always full, never empty, sometimes full. Who am I?
A glass of water.
Let's listen to it again. Always old, sometimes new, never sad, sometimes blue. Never pushing, always full, never empty, sometimes full. Who am I?
Who am I?
Yeah, who am I?
Yeah, hard.
These are good answers, but no. Okay.
Wait, no. I want to do one.
You got one to give to share?
I got one.
Wait. So we never answered yours. So keep them. If we don't have the answer immediately, save them, and we'll answer it at the end of class. Okay? I know the one that you said twice in a week and once in a year. I know the.
No, I got another one.
Okay, what's the other one?
Okay, so this is story.
Okay.
So
We don't have a lot of time, but that's okay. It's okay. It's okay.
You're driving in the car, right?
Oh, I know this one.
Car
Keep
is
going.
black.
Okay.
All the street lights are busted. All of the none of the porch lights are on. You're driving down your street. A black cat runs out in front of you, and you stop. How did you see it? I said your headlights are busted.
Say the story again. Say it again.
You're driving in the car.
Mm-hmm.
Your
Oh, I know the answer. I know the answer.
Stop.
I got it. I'm not gonna say it. I think I got it. Anybody got it?
It's daytime.
Yeah, that's what I was thinking. Yes, yes. She didn't say it's night.
The thing that makes you think that
'Cause it's black.
saying the lights are
Yeah.
out and you see things
It's
that are
black. You kept saying black. She was
are-
priming us. I was like, she's priming us for something. I was like, how can we get some light? That's
Can we get some light?
that's awesome. But see, yeah, that's awesome. Okay, let's get back on task. What's the time?
Just go to the next.
Well, yeah.
Meanwhile, the people at home listening to the riddles.
All right. So I think I've decided for my extra credit for the people at home, and you know, I'll do something for you all here. Yeah, probably. But so if the people are home, if anybody at home has listened to any of these riddles that we just did, if you send me the results to any of these riddles, I can give maybe double bonus points, max. So 5 points each. So you can get a total of like double bonus points. Okay.
We did a couple of riddles.
So okay. So now I'm going to move forward. If you want to know the results to any of them by the end of class today, if you bring it to my attention before we leave, I'll try. I'm watching the clock, so I know that we have. I only want to go for about another 10 minutes. Okay. So we've seen this one. Okay, I'm going to let that be. Symmetry. What does it mean for? What is symmetry? What does that mean?
Same on both sides.
Yeah. So you can cut it in some kind of way, and one side is going to be a reflection, or it's the same as the other, right? What are some examples of things that are symmetric in your everyday life? Rectangles are symmetric. You can cut it vertically, horizontally, circle. You cut a circle through the center. You know, from one edge to the other through the center is going to be symmetric. Stars. You know, there's a lot of things that you can cut and it be symmetric. Test for symmetry. So now, this graph is not proper, but if we had a parabola, so if we had a U-shaped graph, would you say that that's symmetric about the x-axis, the y-axis, or the origin?
About the y-axis.
Right? If you have a U-shaped graph, we can if you cut along the y-axis, the left side matches the right, or is it a mirror image of the right? Does that make sense? So if we're going to do a test for y-axis symmetry, so look at this, real quick. If we watching the clock, let's go like here, I guess. So if my pen is irking me, I think it's some update that they did is why it's behaving that way. Like this is a new pen and they did an update, so I can't tell if it's the pen or if it's the update. But anyway, if we have something like this, and say our graph looks something like this, right? So now, when x is 2, for instance, what's the corresponding y? 4, right? So this is f of x equals x squared. So when x is 2, then y is 4. What about when x is negative 2? Right? So if x is negative 2, y is also what? So what changed? Even though both of these points have the same y value, what changed? X value. So when we're talking about y-axis symmetry, what changes, the x or the y? X, right? So if we want to do a test for y-axis symmetry, we change the x. That's how we do it, right? So it's as follows. We have this. We want to test for y-axis symmetry. So we're going to change x to negative x and simplify it. If we get the same y value, then that means we're talking about y-axis symmetry. Does that make sense? Okay. So again, just like in life, if you're not looking for it, you're not going to see it. You know, one of my mentors would say, focus your mind, focus your eyes, focus your body. You know, so I know I kind of have a sense of what's going on. I'm not going to press it, but you know. So now if we're going to do a test for y-axis symmetry, again, change the x. Change the x. Focus your eyes, focus your mind, focus your body. So now we change the x to negative x. Notice we got the original back. That's an example of y-axis symmetry. So if we have y-axis symmetry, we change the x. What do you think we change if we're talking about x-axis symmetry? Change the y, right? So if we're going to do a test for x-axis symmetry, let me see. Test for symmetry with respect to the x-axis and where is it? Here it is. So to test for x-axis symmetry, we change y to negative y. If we get the original, then yes. If not, then it's no. Pardon?
Is this 2-7 right?
This is 2-7.
Okay.
So I see the clock. I'm going to kind of move forward. Okay. So again, x-axis symmetry, change y to negative y and simplify. Y-axis symmetry, change x to negative x and simplify. Okay? If you get the original, then it's a yes. If you don't get the original, then it's a no. Okay, so if y-axis symmetry, we change the x, and x-axis symmetry, we change the y, what do you think we change if we're talking about symmetry with respect to the origin, if you use your intuition? So if we're talking about y-axis symmetry, we change the x. If we're talking about x-axis symmetry, we change the y. What do you think we change if we're talking about symmetry with respect to the origin? What's the opposite of that?
Everything.
Yeah, you change both of them. That's exactly it. Yeah. So you were close. And again, practice going with your first mind. Don't second guess yourself. It's fine. So now, when we start talking about symmetry with respect to the origin, we change both the x and the y. All right? Let's see if we got it. We did that already, so I'm going to leave that as an exercise. Leave that as an exercise. See, notice, if we change either x or y here, this is an example of something that's symmetric about the x-axis. Sorry, about the origin. Symmetry with respect to the origin means that whenever you have x comma y, we also have negative x comma negative y. So even if we change both, it's still going to give us a point on the graph. So no matter what x, y you choose, when you go to negative x, negative y, that result is also on the graph. That's what we mean by symmetry with respect to origin. Another way you can look at it, if we took the top half of this parabola, right? Oh no, undo. So symmetry with respect to the origin is like if you took the top half of the graph and rotated about the origin, it'll match. That's about the best I can do. It'll match the bottom half. Does that make sense? So symmetry with respect to the origin, another way we can look at it, if you take the top half of the graph, rotate it 180 degrees, it's going to match the bottom half. So there's two different ways of looking at the same thing. Okay? Let's keep moving. So we know how to do that. I'm going to have to leave that as an exercise. All right. If this graph is proper, say, is it symmetric about the y-axis? Yes or no? If you fold along the y-axis, will it match up? No. If we fold along the x-axis, will it match up? No. If we take the top half and rotate it about the origin, will it match the bottom half? No. So if we did a test for symmetry here, it should fail all three tests. Okay. So if we test for y-axis symmetry, we change x to negative x, we won't be able to get back the original. If we're doing a test for x-axis symmetry, we change y to negative y, we won't be able to get back to the original. If we're in a test for symmetry with respect to the origin and we change both, we won't be able to get back the original. So this has no symmetry. Okay? So the origin we discussed already, and it's the same kind of deal. I'm going to let that be. These graphs are not proper. Okay. So even function. So now, intuitively, if I say a function is even, what do you think? What comes to your mind when you say the function is even? Let me think about it. So I know when I first heard about a function being even, I thought that the highest power was a 2. And my professor was like, no. He wouldn't tell me what it was. And it took me a long time to figure it out. I don't know why I wouldn't just look it up. But I didn't just look it up. And I kept getting it wrong, and he wouldn't tell me. A function being even means that it's symmetrical about the y-axis. So even, it does have a play on the 2, but that means that it's going to be symmetrical about the y-axis, similar to the parabola. So it's similar to the highest power is a 2, but to be more accurate, it means that it has y-axis symmetry. What do you think? So if even means y-axis symmetry, what does your intuition say as far as a function being odd? That's fine, but it's wrong. But it's okay. It's okay. Because that feeling, it locks it in once you hear the right thing. That's the whole point of going with your first mind. Because it's so devastating when you get it wrong. You're like, wait a minute. Then when you see the right answer, it sinks in. So that's the whole point. So now, even means y-axis symmetry. Odd actually means origin symmetry. It's symmetrical about the origin. X means that if it's symmetrical about the x-axis, it's not a function. It's going to fail the vertical line test. Okay? But this is okay. So even means y-axis symmetry. Odd means symmetry with respect to the origin. I'm going to leave this as an exercise. You can do this. You can do this. You can do all this. I'm going to keep moving. Translations. Okay. We kind of need to talk about this. I'm going to keep going with this. So now, before we said which kind of manipulations were vertical manipulations? Inside or outside? outside, right? It's the same thing here. If we add a positive on the outside, intuitively, should it go up or should it go down? Right. So outside manipulations, follow your intuition. If we add a positive on the outside, it should go up. If we add a negative on the outside, it should go down. That's correct. So now, outside follows the intuition, so the inside does the what? Opposite of your intuition, right? So now, if we add a positive on the inside, should it go to the right or should it go to the left? What does your intuition say? If you add a positive on the inside, which way should it go? It should go to the right, but it actually goes to the left. It's the opposite. Remember? Well, I'm playing on intuition. So intuitively, if you add a positive on the inside of your function, intuitively you would think it would go to the right in the positive direction. It actually goes in the opposite direction. So it goes to the left. If we add a negative on the inside of our basic function, now which way should it go? Intuitively, it will go to the left, but it should actually go to the right. So inside is the opposite. That still holds. Okay? Let's keep going. So I'm going to let this be. You can get through this. This will, once you work these, you'll see it. See, notice. Look here. What's the basic function? So if this were, so the basic function here, or the original function is g of x equals absolute value of x minus 4, right? If this is the original, right? What's the basic function? Is it identity, squared function, cubic function, square root function, absolute value, cube function? This is absolute value function, right? So what's the basic shape? It's a V. Now, we said we added a negative on the inside. So intuitively, this should go to the right. Without this discussion, you might think it goes to the left, but it actually does the opposite. It does the opposite. He's like, getting on my nerves. It's like this every day. It's so funny. It actually does the opposite. So it goes to the right. So when we add a negative on the inside, it goes to the right. So what this is going to be a V, but we're going to move it right by 4 units. Okay? These are called rigid transformations. Okay? If we add a positive on the inside, which way does it go? To the left. Inside is always the opposite. Okay. So I'm going to let this be. That's what all of this stuff is saying. Okay. Really quickly. What's the basic function? What's the basic shape? Ignore the manipulations. So the basic function is a V, absolute value. Let's work our way from the inside to the out. We add a positive on the inside. Which way does it go? It goes to the left by 3 units. Right? So that's it for the inside manipulations. So we have a V at the origin. This says go left 3 units. We multiply the outside by a negative. What happens? It flips from up to down because it's on the outside by negative. So all the y's go from positive to negative, right? So now, if we're at the origin, we went left 3, then we flipped up and down. Now, what does that plus 1 tell us to do? Up by 1. Yeah, sorry, I gave you the answer. But yeah, so then it goes up by 1. So it's outside manipulation, means it's vertical, follows the intuition, so it's going to go up by 1. So those are the 3 transformations going on here. This says start with the V-shaped graph with the V at the vertex at the origin. It says go left 3, flip it up and down, and then go up 1. That's how we do it. We work our way from the inside to the outside. Okay? Let's do one more, and then I'm going to close this out. Yeah, let me do one more, and then... Okay, so this one, for instance. What's the basic shape? Oh, wait, didn't we just do this one? Okay. So, you see, we went left 3, flipped it up and down, and then up 1. Let's do it again. Let's do another one. What's the basic shape? V. Actually, I need to do a manipulation on this one. I got to get this one in the right form. So, if the original, let's go like this. I think that's fine. If the original is h of x equals the absolute value of 2x minus 4, right? If we factor out the 2, well, this is the same as 2 times, well, x minus 2, right? Is that right? Okay. So then this is actually the same as 2 times the absolute value of x minus 2, right? Now, let's do it from this form. If this is proper, right, suppose this is right. Suppose this is right. What's the basic shape? It's a V. If we add a negative on the inside, which way does it go? To the right. Remember, it's always the reverse. Left is negative x. You got to reverse it when you're on the inside. So it goes to the right by 2. You missed it because you were out. So you're gonna have to do the best you can. Yeah. You're gonna have to work together and figure this out. Hang tight. Hang tight. So now we add a negative on the inside. It goes right by 2. Yeah. Yeah. I'm saying that on purpose because that's the way the definition says it. So in this example, we're adding a negative on the inside. That means it goes to the right by 2. So we have a V at the origin. It goes right 2. Now we're on the outside. So outside manipulations, is it side to side or up and down? Up and down. If we multiply on the outside by a number larger than 1, we're talking about a vertical what? Vertical stretch. So what's going on here, the V is at the origin. It says to go right by 2 and then do a vertical stretch by a factor of 2. If we didn't put it in the right form, we could have been led astray. That's why I paused on this one, because I knew we had to put it in the right form. So what we had to do, we had the V. It says to go right by 2 and then a vertical stretch of 2. Let me check the answer and make sure I'm correct. Okay, so we said, wait a minute. Yeah. We went right by 2 and then we did a vertical stretch by a factor of 2.
So you took out 2.
I factored out the 2, yeah. Because if we didn't factor it, it's tempting to say, oh, right 4 and then a horizontal compression by a factor of 2. And the horizontal compression would have been fine, but we would have had the wrong horizontal translation. A horizontal compression by a factor of 2 is the same as a vertical stretch by a factor of 2, right? So that would have been fine, but we had to get the proper left and right.
So how do you know that?
Experience, repetition. That's the only reason I knew that, to do that. Because I've done it so many times, I just knew.
What happened to that negative?
It's still there.
So why isn't it negative 2?
The negative 2 means go to the right. The inside is the reverse of your intuition.
No, I'm talking about the negative on the outside.
Yeah, I think we just haven't gotten there. So if we multiply the outside by a negative, it's going to flip it up and down. Did it make a mistake somewhere? Yeah, one of those is a typo. That negative might not supposed to be there. I think that negative is not supposed to be there. But if it were there, it would flip it up and down. Yeah. Okay, we're about out of time, so I'm not going to be able to get to the next one. I'm just going to go ahead and finish this out. Okay, this one, really quick. Is the next one quick? Okay, look. What's the basic graph here?
It's a linear. No, it's the parabola.
It's a parabola. It's a U-shaped graph. Now, is there anything inside the parabola going on?
Yes.
Are there any parentheses or anything like that? No, right? So there are no inside manipulations. So all of these are outside. Outside manipulations are what kind of manipulations? Vertical, right? So all of these should be vertical. Does vertical follow your intuition or is the opposite of your intuition? It follows. So whatever the natural thing that works, it should work, right? So we should have a U-shaped graph, right? What's the thing that's closest to the squared? The 1/2, right? The 1/2. Should it be a vertical stretch or vertical compression? It should be a vertical compression. Which way do we flip it? We flip it down, and then the +4 means do what?
You move it to the right. No. It's to the left.
Up, because it's outside. Outside means up and down. If that +4 were inside the parentheses, it would be left and right. It would go to the left by 4.
Everything is
So now let's bring it together. Let's bring it together. So it should be a U-shaped graph. It should be a vertical compression by a half. It should be flipped up and down and then go up 4. So it should have a wide graph that upside down. See that? Wait. We're out of time, so I'm just trying to wrap it up. at this point. Graph of this defined by this is shown. Use the graph as sketch. Okay, so now this one, we have this weird graph. We want to apply. I'm going to leave this as an exercise. You can do this. So it's going to be an exercise. I'm going to leave it for you. Yes, you can. Because all you got to do is the same stuff we've been doing. Just keep doing the same stuff. Outside manipulations are vertical. Inside is horizontal and the opposite of your intuition.
This time it's inside, right?
Yeah, that +3 is inside. So if we add a positive on the inside, what should it do?
It's going
So intuitively, it should.
No, it shouldn't because it's inside.
So inside is the reverse. Yes. Intuitively, it says to go right by 3, but again, it's reverse because it's inside. So it should go left by 3. So if you follow that bottom, the origin, oh, that's a different one. Where's the original? Wait a minute. I want to see the original. Where's the original? Right. So if we said a plus 3 on the inside, if you look at the origin, that should go left by 3. That's not that one. This one. See? Notice it went left by 3. Okay? So again, this is why I'm leaving this as an exercise. You actually know this. Just do the same thing. Don't get bogged down. Just keep doing the same thing and catch the changes. I'm going to stop there. Let me go ahead and load this. So we finished 2.6, 2.7. We actually have one more section that I want to talk about for the quarter. We'll do it on Monday. I'll go through it as quickly as I can. Or I might do a video lecture. I might just go ahead and do a video lecture. That way we can use Monday as a review. I want to review for the final. So that's what I'm going to do. I'm going to leave. Actually, there's already a video loaded. So there is a video loaded for 2.8. I'm going to leave that for you. So as of this moment, I don't want to do any more new material. You're responsible for 2.8. If anything is not clear, you got to reach out to me. You got to hound me. You got to email me. Your job is to ask me questions. My job is to accurately, precisely, consistently, correctly answer your questions. Don't let me lie to you and don't let me tell you false truths, right? So I'm going to give you what I believe to be the truth. You got to verify and make sure that it's right. But your job is to ask questions and be sincere and genuine. If you're not asking questions, that has a meaning. I'm going to let that be. So there's a video that's already loaded for 2.8 on Moodle. You can use that for your instruction for 2.8. The assignments for Chapter 2 are already loaded. The study guide for Exam 3 is loaded. For Exam 3, you're only responsible for the first half of Chapter 2. If you're comfortable with my study guide, you should be okay for my exam. For the final exam, use your old study guides, old exams, anything that you see on My Math Lab. I'm not going to print out any PDFs for the study guides. I'm not printing those out. If you want a study guide, you got to go on My Math Lab and get it from there. You got to work that. So what we're going to do, Friday is Exam 3, first half of Chapter 2. Monday is a review for the final. The final is Wednesday. Anybody miss an exam in here? If you miss an exam I know I'm just being thorough and complete. Final is Wednesday. Friday after the final is a flex day. If you miss an exam, you can make it up on that day. You said you missed the first exam, is that correct? Attendance, I think it went around, so make sure your name is on the attendance. We got hang tight. 2, 4, 6, 8, 10, 12. Are there 2 people right there? Yeah or no? Okay. It should be 13. Hang on. 1, 2, 4, 6, 8, 10, 12. Okay. So it looks like everybody's here. You guys were a great audience today. Since you're such a great audience, everybody in the house gets double bonus points. Okay, we got a couple of minutes. I want to try to answer some of these riddles. Anybody get the... Okay, what was yours? How many what?
Wait.
Say it again.
30,000 filled and 28 chickens. How many did?
How many what?
There's 30,000 filled and 28 chickens. How many did?
Did it what? What?
Dented.
Oh, wait.
What is it?
28 chicken. And then like
So 2. So 2, right?
It's 30 cows.
28 chickens.
Oh,
28
chickens.
So 2.
It's a play on words like 8.
Oh, 28 chickens. Oh, so 10.
Yeah.
Oh, okay. I couldn't get it. I was like, what is he saying? I thought you meant like chicken, like they ran off. And so,
That's why I said chicken.
Yeah.
But then I was like,
so when you said, I thought you said 28 were chicken. You know, yeah. So I thought you said 28 ran off. You know what? You know what? Now I was afraid of 7, right? Okay. Okay. What was the other ones?
That's the elementary school.
It was like 7.
We already know that one.
I forgot.
Okay. We have some others that we talked about earlier. Twice in a week and once in a year. Yeah. Okay. So the answer is
No,
E.
don't
It's E. We just answering the riddles because for the audience. Y'all want any other answers before we part ways?
What's your answer?
Which one? Both? Okay, so what's greater than God? Literally, what's greater than God? What's more evil than the devil?
Oh, nothing.
What do the poor have? What do the rich need? What if you eat, you'll die? That's the answer. Okay. 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 So then, if you eat nothing, you will die. Okay. So then another one. Here's another one. The other one was always old, sometimes new, never sad, sometimes blue, never pushing, always full, never empty, sometimes full. Who am I? Not water.
Air.
Getting closer, but it's not air. Go further.
Ice.
Go further. When?
Trees.
Keep going further.
Fires.
Did you get?
World.
What'd you say? What's up in the sky?
Clouds.
Not
Sun.
not the sun, not the star,
Humanity.
not the
Stars.
not the stars.
The moon.
The moon.
What? Okay, repeat it again.
Always old, sometimes new, new moon. Never sad, sometimes blue, blue moon. Never empty, sometimes full. Never pushing, sometimes always full, the moon.
I didn't get that last
If
one. The moon.
if time flies like an arrow, what does fruit fly like?
A fly. A dragonfly.
If time flies like an arrow, what does fruit fly like?
An apple.
Yeah, fruit. I'm not saying it right, but yes, a fruit. It's like fruit. If time flies like an arrow, what does fruit flies like? Something like that. It's fruit.
It's fruit. What does fruit fly?
What is a fly?
So a fruit fly.
What is a
fruit fly?
It's supposed to be what does a fly fly like?
Oh, that's how you say it. Okay, so I said it wrong. If time flies like an arrow, what does a fruit fly? No, what does a fly like? Wait, what?
What does a fly like?
What does a fly fly like?
What does a fly?
If time flies like
An arrow.
if time flies like an arrow, what does
a fly like? Get it?
what does a fly like?
What does a
If time flies like an arrow, what does a fly like?
fly
He's
like?
saying what is an actual
Fly like.
Oh,
But I think
God.
you're trying to say what is a fruit fly?
Yeah, I'm trying to say it in a similar way. I can't think of any others. Any others before we part ways? Okay, so everybody in the house got double bonus. We're in the home stretch. Do your best on exam 3. There will be a surprise or two. We'll talk about a surprise or two after the exam. Let's get through exam 3, and then we'll have a discussion after that. Okay. Otherwise, it was a great session today, everybody. Good luck with everything. So we're done with the new material that I wanted to do for the quarter. The rest, we're studying and testing. Again, you could be anywhere. I think we talked about the grading. Did we talk about grading? No. We'll talk about that after exam 3. Let's get through exam 3, and we'll have a discussion about grading. Okay? But just keep in mind, I want you to be aware, at this point, anything can happen. You can be anywhere on the spectrum. And if you did well on exam 3 and my final, you can completely turn your grade around. You could be at the bottom, and you can finish with an A. Anybody can at this point. Okay? I'm giving you that little bit of encouragement. Okay? All right. Good luck, everybody. Have a great weekend. Let me go ahead and load this. Sorry, not weekend. I'll see you Friday. All right? This goes to college algebra. It's in the box. All right. I'm going to stop streaming. And so with that, with my online audience, we will end the session here.
From one beautiful mind to another.
From one beautiful mind to another, enjoy the rest of your day.
Thank
All right.
you.
Thank you.
Goodbye.
So much excitement. I'm so excited to...